So now it's time to start the live demo that is related in order to design the control loop for the. Sorry, this is a mistake. Okay, this is for the induction three-phase induction motor. So the challenge is that the motor's control plays a key role across a wide range of applications, including automotive, industrial, aerospace, and renewable energy sectors. Typical in this architecture, we have a double loop. The inner loops try to control the torque that it's proportional to the current, and in the outer loop, we try to control it or regulate the speed of the motor. So the induction machine is a little bit complex because we have this control structure is based on DQ control. So in that case, in the induction machine, we try to separate the axis. For example, the D axis try to control the flux of the converter, the rotor flux, and the Q axis try to regulate the torque of the motors. So I want to show you a little bit later what is the control structure. But in that case, in this example, we'll start with the PSIM simulation. I already have a PSIM template with an induction machine. Then I have to open the SmartCtrl, and I will use the equation editor section, because in that case, I know the transfer function of the current plan, and also I know the transfer function for the speed plan of the converter. So after I design or after I tune the PI compensator for the torque and speed loop, then I copy the parameters, the constant, the proportional constant, and the TI of the PI compensator. I copy the values, and I try to see in PSIM what is the transient response of the converter, in order to ensure if the point that the operating point that I selected is stable or not. So this is the procedure that I try to follow in this section, in this live demo. So this is the typical control structure of the indirect field oriented control of an induction machine. So in that case, we have a three-phase inverter, and the first things that we have to sense is sensing the current, the three-phase current. As you can see here, we have a park transformer in order to pass from the ABC to DQ axis, as you can see here. But one of the problems is that we have to know the phase. So the main idea here is that we have a rotor flux. The rotor flux has a speed. This speed is called the synchronous speed of the rotor flux. So in that case, we try to use from the DQ model of the three-phase induction machine, we try to implement a flux observer in order to estimate the synchronous speed of the rotor flux. So I try to show you a little bit later, but after I estimate the synchronous speed, then I use an integrator in order to know the phase. So in order to know the phase of the rotor flux, or the position of the rotor flux. In that case, this is the parameter that I used in the DQ transform. So as mentioned before, we have two axes for the current control. The D axis is related to control the flux, the magnitude of the rotor flux, and for the Q axis, we have in order to try to control the torque of the motor. So in that case, the torque will be imposed by the second PI, for the outer loop. this PI control the speed of the rotor. This is the mechanical speed of the rotor. So we try to regulate, impose the torque, and then we have an inner loop that try to regulate. So also, as in that case, in this control structure, we have to sense in the three-phase current and also the mechanical speed of the rotor. So this is the flux observer implementation. The flux observer implementation try to operate like to a PLL, a phase look and loop. That is typical. That is very typical configuration that you can find in three-phase inverters. So in that case, from the Q model of the motor, you can see that the first step, we try to estimate the slip speed. This is the phase things, because we have a rotor flux here that has an synchronous speed. So we try to estimate the synchronous speed of the rotor flux. So as you can see here, we know the mechanical speed of the rotor. That is this. You can, because you can sense it directly from the motor. And then we try to estimate the slip. This is the point. So the main idea is here, because we try to align the rotor flux with the d-axis of the DUQ control. Why? Because the torque of the induction machine depends of the D and Q component of the rotor flux. So if you align with the D-axis, you can make zero this term, and also you can simplify the torque expression. So that means that with the D-axis, we try to decoupling the axis. So that means that with the D-axis, you can directly control the rotor flux, and for the Q-axis, you can really control the Q current. You can control directly the torque. So this is the main idea here. So what is the reason why? This is the reason why we try to synchronize with the synchronous speed of the rotor flux. So, and also another thing that is important in this observer implementation is that the mechanical speed, you have to multiply for the pair of poles divided by 2 in order to estimate the electrical speed. Because all the parameters will be in radians per seconds. So after that, you can implement an integrator in order to estimate the phase. So this is the main idea. After that, also, we have some feed-forward compensation. This represents this stage of the control structures. The feed-forward compensator is try to decouple the axis, because remember, when you use the Q transform, you always find a coupling axis, and with the feed-forward, we're trying to decoupling this axis. So they try to get that the will be separate the components. So in that case, this is parameters, all the constants or all the variables that you can find here depends on the motor of the motor parameters. You can find this parameter, for example, in the manufacturer datasheet, or maybe you can measure with some test on the motor. So in that case, if you implement the decoupling axis, the feed-forward compensator, and also you can compensate the modulator gain here, you can see that now the plant of the current plant is just this expression. It's very compact transfer function. I think it's a little bit easy to design the control loop for this converter plant. This is a first order plant. And in that case, one of the problems here, or maybe that you can, one of the things that is very important is you have to define the current reference, the D current reference that is related to the to the rotor flux. So in that case, the reference, you can, as a first step, the reference current for the D-axis is estimated based on the motor no load current test. So this is the first approximation. And then, for example, if you want to implement a field weakening control, you can define an outer block here that you can impose the new current reference, the new current reference in that case. Because remember, when you increase the speed over to the nominal or rated speed, you have to decrease the flux. So this is the main idea of the field weakening implementation. For the outer loop, this is the speed loop. Remember that speed loop is implemented for the Q-axis, as you can see here. This is the speed loop. In that case, this is the transfer function that we have to contemplate. We have the inertia for the machine, and also in this example, we are contemplating that the load torque is constant. So in that case, in a small signal, we can reject, or we can not take into account the load torque. This is the reason, but I consider zero here. So in that case, remember, the main idea here is that the D-axis will start first, and then you can, after some time, you can impose some speed reference. The main idea is here that when you try to impose a speed reference, these parameters will already be stable. So in that case, you can consider all this part like a constant. The main idea here is like this expression is very similar to the in order to control like a DC machine. So this is the main idea, because only with the Q-axis you can control the torque. So this is the main idea. And also remember that the outer loop, you have to contemplate the inner transfer function. This is the closed loop current. And finally, we have an NPI. So after that, I try to use the SmartCtrl software. Remember, if you go to File, you can find here the initial dialog window that I showed you before. In this section, you can find the predefined topology, the generic, this is for if you want to import from the frequency response from a TXT file, and also you can find here the equation editor. In that case, I will use the equation editor function. So I click in this section. Then this is the next window that appeared. This is the plan equation editor. So if I click on editor, here I can write the converter plan. So in that case, I have to write this plan of the converter. So I already have this file here. Let me copy this part. So, okay, here this is the parameter of the motor. Also, this is the variables that I show you here. And this is the transfer function that I have to write here. So here I have the current plan, and also in the equation editor you have to define the return function in order to tell to a SmartCtrl what is the converter plan that it has to take into account in order to design the control loop. So in that case, I click on OK, and also I have to define the switching frequency. In that case, is 10 kilohertz. I click on compile. As you can see, this is the frequency response of the converter plan. This is a first order transfer function. After that, I have to click on OK. Now I have a second equation editor. This is related for the sensor. In that case, this is for the current sensor. So in this example, I consider a unity gain. Remember that I have to put a return each eye. Click on compile. This is this here you can write the transfer function of the sensing change. Then I have to click OK. And now you can select one of the predefined compensators, the type 2, type 3, PI, and also you can define the question editor for your own transfer function. In that case, I select a PI. Here, this is related in how to define the modulator gain in SmartCtrl. This is the way that SmartCtrl estimate the modulator gain. So if I want to consider a gain of 1, I have to set a peak value equal to 1, the valley value equal to 0, and the rise time equal to the switching frequency. In that case, the modulator gain is equal to 1. So I consider a modulator gain equal to 1, remember, because I have to contemplate also here the gain of the modulator. So in that case, I select 1, 0, and also here 100 microseconds. Click on OK. And now I have to select one point in the solution maps. Remember, the solution maps represent the crossover frequency and the phase margin. And I want to select 1 point, for example, here. Click on OK, and that's it. So here you can see the transient response. This is a small signal transient response, and also you can see here the frequency response, the body plots. The pink trace represents the open loop transfer function. So in that case, for example, I want to also you can move the cursor here, and also you can define directly here the crossover frequency. In that case, I select a crossover frequency equal to 2 kilohertz and phase margin equal to 50 degrees. So now I have to copy these two values in the PSIM simulation. So in the PSIM simulation, I have the three-phase inverter. Also here, this is the induction machine model. And here you have to set all the motor parameters, as you can see here. This is a sensor, and this sensor gives you the speed in revolution per minute. In that case, I multiply with the gain because all the model is in radians per second. So in that case, this is the transformation. And also here we have a mechanical load. In that case, as I mentioned before, I set constant torque load. In that case, it's like a 5 Newton per meter. So then this is the PWM modulation. We have the part transform. This is the decoupling axis here, as you can see here in this part. This is the modulator gain, and also we have the PI. So in that case, I have to define here the values of the PI. So in that case is 138.629. And the TI, for example, 93.783 micros. Okay, so I want to save this. And now it's time to define the parameters of the PI for the outer looping. So now I open SmartCtrl again, and I go to Files. I want to click on in the initial dialog. Again, I go to the equation editor. I have to define the converter plant. Remember that for the speed plan, we have to contemplate the transfer function of the current plan, and also the constant of the torque constant, and also the inner loop of the currents, and the sensor if you have. So in that case, I already have the transfer function here. This is the parameter of the motors. This is the parameters that I put here in the for the inner loop. This is these values. This is the calculation of the constant torque and also the torque constant, and also for the variables for the inner loop. This is the PI compensator of the inner loop. This is the current plan, and also this is the closed loop of the current plan, as you can see here. And finally, the transfer function for the outer loop is this. You have to multiply the torque constant, the inner loop, and also the speed plan. And finally, we have to put a return function of the speed plan transfer function. Click on OK. Remember, I have to select here 10 kilohertz. Click on compile, and this is the frequency response of the outer loop. Then I have to click OK, and here also I have to define the transfer function of the speed sensor in that case. In that case, I also consider a gain of 1, a unity gain, return to HW. Click on compile, and finally click on. In the last step, I have also to select one of the predefined compensator. In that case, I select the PI compensator. And here again, I have to define a converter plan, a modulator gain equal to 1. Remember that the peak value is equal to 1, the value is equal to 0, and the rise time is equal to switching frequency, period. Sorry, switching period. So in that case, I click on OK. And now again, I can select one point, click on OK. And now I can select here a crossover frequency. So in that case, I select what crossover frequency equals to 300, and also here like 40 degrees, for example. So I have to copy the key P and TI values of the other loop. So I select here. This is 10.608 and 4052. 452.034 micros. So now I try to put this is the reference. This is the step voltage reference. Sorry, the step reference of the speed of the rotor. In that case, I start the reference after 100 milliseconds in order that first try to that the DQ, sorry, the D current, we already achieved the reference before I inject the speed reference. So I try to show you. First, let me put another step here, for example, 10 radians per second, and also in 1 second, for example. Let me run the simulation. So this is the D-axis current reference, and remember the Q-axis current reference is imposed by the outer loop. So in this part, I implement the flux observer. We are sensing the three-phase current, the stator current. Then I try to apply the DQ transform, and also here you have the DQ current. This is the transfer function of the flux observer, and here we are sensing the mechanical rotor. Then we have to multiply by the poles, the pole pairs, and here in that point we have the rotor, the synchronous speed of the rotor flux. And then I have the integrator. This operate like a VCO in order to estimate the theta that I use in the DQ control. So the simulation will finish. In that case, you can see this is the starter current of the machine. If you can see here the speed, this is the speed that achieves the reference that we inject, and also you can see here the axis current, and also you can see here the axis current. So as you can see here, that I tried to show you before is that the reference of the pit is injected after some time in order that you ensure that the D current is stable, in order to try to consider this is a constant, like a constant value. This is the main idea here. So as you can see here, we have the current reference and also the axis, and this control loops is stable. As you can see here, this is the three-phase current, and that's it. And the last thing I try to implement is just, for example, if you want to measure the frequency response, in that case, I have to put perturbation here. Okay, I have to select a sine wave here. Oh, sorry. Here, let me put a name. This is one. Amplitude 0, frequency 0. Okay. And I want to put an AC sweep block. And also I want to put an control, let me, others proof AC sweep proof loop. So in that case, I put here, and then I have to define the start frequency, and also this is the end frequency. In that case, for example, to 4 kilohertz, and in the amplitude, I point. This is the amplitude value. So that's it, and then I click on run. Now the AC sweep the AC sweep is running. We have to wait a little bit. So in that case, we are injected a perturbation in the speed of the rotor. This value is the sensing. We are injecting a perturbation, and we try to measure the loop. So that means that we try to measure the pink trace. The pink trace considered the PI, the inner current loop, also the torque constant, and the speed reference. Sorry, the speed plan, and also the sensor stage of the speed. So this is the open loop transfer function. As you can see here, this is the frequency response that we get from the ACC function. And you can, if you go to edit to view data point, go to file, save as. You can save here in the txt file here. I want to put here, this is the T transfer function. Click on save. And now you can open this in SmartCtrl. For example, if you go to files, in this option, you can find the import merge. This is in this window, you can add a txt file. This is the open loop transfer function. You can change a color. The txt file, we have to select the file. In that case, I think it's this. Click on open. Click on OK, and then you can click on Apply. As you can see here, both transfer function match very well. We have some little bit different here, but it's related to the also to the time step of the simulation of the PC. So, but in that case, the crossover frequency and the phase merger match very well. That it's predicted from the smart control. So this is all the thing that I try to show you today. I think that I hope that you enjoyed this webinar, and thank you very much. And if you have any question, please let me know, and you can write on the chat, and that's it.